I'm beginning this series of lectures with as pedagogical as possible introduction to the subject, with a viewpoint which is not the usual one which you encounter in the PDE community. It's in a certain sense closer to the viewpoint of a control engineer for finite dimensional linear spaces. Nevertheless, to generalize these very basic objects to system described by PDEs, we need some notions of functional analysis, and we need also to construct a certain framework, which will be the scope of my first lecture. So this first lecture will contain very few new results. It will essentially be the basis of presenting the new ones in the 3 lectures to come. So the general aim is to cover subjects which go from a very introductory material to new challenging topics and to open questions. The 4 lectures will essentially follow the plan which is here. It depends on how, which will be the velocity with which I will be able to advance. So the first one today, it will be admissible control operators, or equivalently what's called well-posed control linear time invariant systems. So I'm not at all speak about control practically. So anyhow, not about controllability or observability. The second lecture will be devoted to the introduction of reachable spaces, to some general properties of these spaces, and to their connection with the various controllability types. The focus will be on examples on which we have recent major advances. It's the heat equation. Strangely enough, such a simple object, the heat equation in 1D, it's only very recently that we have obtained a precise characterization of its reachable space. And it's the first significant example in PDEs where we succeed to do that. The third lecture will be devoted to frequency domain methods, which are also called how-to-type conditions. This is also inspired from finite dimensional control theory. How to test being an alternative to the the well-known Carleman test for controllability and observability of differential equation system. And I will end up with a 4th lecture concerning time optimal control problems. Here I will mix up some classical results, namely on heat equation, with some very recent ones on dispersive type equations. The today lecture will essentially be based on the book Maity was gentle enough to mention. So what I will try is to, at least in the very first part of the talk, to make a really shortcut, but really very short, in the first part of this book. And in this way to introduce all the notions in a short time. And if somebody really wants to have detailed proofs, they are in there. So I end with a general introduction. The next sections of the today talk will be a very brief introduction to operator semigroups, then to the definition of well-posed linear time invariant system, control linear time invariant systems, which or equivalently of admissible control operators. And then I will furnish some examples, not only a system which satisfies this definition. Any question? System satisfying this definition, but also with some explicit formulas which will be very useful, namely for the tomorrow lecture. So let me begin now the math part. It will be a lot of functional analysis at the beginning. The definition of an C0 semigroup or strongly continuous semigroup or operator semigroup, all this means the same thing. We will look to this notion on Hilbert spaces, although that people study it, of course, also in a Banach space setting. But for control theory, the Hilbert space framework is more convenient. So it's a family of operators which are bounded from X to X and which have these phi properties, which are well known. So a small t equal to 0, I have the identity, then that's this what's called the semigroup property. And then strong continuity is the last one, which should be distinguished from what's called uniform continuity, which would mean that I have here the convergence in norm of TT to the identity operator. This is a much too strong property, which will never be true for PDEs. And then we have the notion of generator. The generator is an operator which is defined on all these points Z where this limit exists, and the value of this limit is called AZ, the value of the generator at Z. In the case which I mentioned, when my semigroup is uniformly continuous, this DFA will be all of X. So I'll have just an ordinary differential equation, classical one, linear, on the Hilbert space X, which does not, let's say, require any special treatment. It can be a discussion which is rarely done when we apply these concepts to PDEs. What should we begin with a generator or with a semigroup? Of course, PDE people would tend to say with a generator, because when I have an evolution PDE, I will have some equations involving a differential operator A. It's not always so clear. Sometimes, but very rarely, it's more convenient to write the PDE than to derive a solution for smooth data, which will be TT applied to the initial data. So we have a semigroup, and then of course we have to understand on which space it acts, and the generator could come after. So these two viewpoints are both useful, and I will address both of them according to the convenience, of course. So the case of uniformly continuous semigroup, which I mentioned, is in example 3, where the semigroup is just the exponential of a bounded linear operator. Maybe the simplest example, where the generator is not bounded, not a bounded operator, so not defined on the whole space, is example 4, which is a shift semigroup, where the generator is given by this formula. In fact, how do I connect this to a PDE? The PDE which is behind that is the most elementary transport PDE, which will be, let us make a notation, dW over dt at t and x. So how do I obtain this semigroup? I try to explain how I obtain it without beginning with an operator. So how I obtain the semigroup directly, which here is more natural. So it will be is equal to dW over tx, the dW over dx at t and x. So this is for x in for t positive and x in 0a, in some interval 0a, and with a boundary condition which will be W of T and A is equal to 0. And with the initial condition, will be W of 0 and X is equal to what should be denoted here by Z of X. I hope I am correct. Okay. And then the solution of this problem, it is easily seen, will be exactly this one. So in fact, what does this PDE say? This PDE says, if I'm doing an XT plane, I put somewhere here A, it's just saying that the function W is constant on what we have here, the characteristics of the problem, which are the lines X plus T is equal to some constant. Okay? So everywhere here it is constant. In all this region, to find the solution in all this region, I have just to go down on the characteristic and meet the initial data, the value at the initial time. And then when I am larger than A, because here again it will be A, these have a slope of pi over 4, although it's not exactly the case in my picture. And then what will happen is that these characteristics, which go from all the other points, will have the same value as on the at x equal to A, where the value is 0. So this, what I'm writing here, this formula for TTZ is W of T and X, nothing more. So I have solved my PDE. I have a formula. Then this is, of course, when I do these computations initially, or people which did this for the first time, very long time ago, assume that the functions are smooth. But now I can ask myself, to what extent can I give a sense to this formula? And in fact, it goes very far. It would go very far to very irregular objects that can even be a distribution. But here we satisfy to say, okay, let us just take Z an L2 function, that the shifted Z will also be L2. And then the dependence on T has to be continuous and so on. So this is a very natural candidate, so, for the semigroup. And the fact that it satisfies the semigroup property is not so trivial as it seems. The semigroup property itself, it's not a problem. The C0 continuity requires a small amount of attention. And proving that this is a generator also requires a small calculation. So this is a situation in which I can construct first my semigroup, but my PDE is extremely simple. It's the simplest one possible. I can give other examples of the similar simplicity, let's say. If I take, maybe this is also an example which can be interesting. Did I write it here? Not yet. So a second example will be if I take the heat equation on an interval. It's an example I will come back at the end with a formula which is quite different. But of course, we should give the same result at the end. So I take a heat equation on 1D. So here I take T positive X in 0 pi. For convenience, my interval is of length pi. I put homogeneous boundary condition at both ends and an initial condition is equal to theta 0 of x, which I assume to be developed in a Fourier series, sum from 1 to infinity of an sine nx. This is why I choose pi here, to have only sine nx here to make it simpler. Then it is not difficult to see. This is the classical Fourier analysis of the heat equation on the interval. The solution of that, assuming that everything is smooth enough, all the conditions are satisfied, will be easily computed to be the sum of n larger than 1 of an exponential of minus n2t sine of nx. And this object, I can renote it by tt of theta evaluated at point x. So this will be a semigroup, the heat semigroup, given by this formula, and which will act on capital X, where X is, for instance, L2 of 0 pi. Here I have multiple choices. In fact, the standard one would be L2 of 0 pi. So, which means that my Fourier coefficients an will be a small L2 sequence. But of course, I can take much smoother or less smoother. It will still be a semigroup. This is a construction which will be explained immediately after. So these are examples where, in fact, I can construct directly the solution. So I have a semigroup. And then I compute the generator. I can compute the generator here. The generator here will be, if I choose this space, I can compute it, and it's not difficult in this case. I have a domain which will be the Sobolev space W22 of 0 pi cap W0, 1, 2 of 0 pi. For reasons which will be clear in the next talks, I prefer this notation for Sobolev spaces with 2 index instead of 1, even if my second one will always be 2. But it's for reasons which are not purely notational ones. And let's say theta 0, will be d2 theta af, will be d2f over dx2. So this is the generator of that semigroup. And a way to establish it, I find first the semigroup, and then I find the generator, which is not the most standard one. Okay, so nevertheless, in applications to PDEs, in general, it is more natural to have a good candidate for A, and then to prove that it generates a C0 semigroup. So it's very rare that we can begin by constructing the semigroup, as I just showed. So it's interesting to know which kind of operators generate semigroups. There is a condition which is necessary and sufficient. It's called the Hille-Yoshida theorem, but it's very difficult to apply in let's say, PDE examples. So here I just made a non-exhaustive list of cases when A generates a semigroup. The operator A is self-adjoint. This was the case here for the heat equation, in fact, although I did not show this. The operator A is skew adjoint. So I don't repeat what self-adjoint and skew adjoint means. I just remind that to define these concepts, I need to suppose from the beginning that the domain is dense. And then I have the perturbations. If I perturb a generator A tilde by a bounded operator, so defined on all the space, I will still have a semigroup generator. This very simple list covers all the examples which we will see at least in my lectures, but I think not only. So in the second case, that's an important one, which will be made the object of my third lecture, essentially of my third lecture. in fact, the semigroup can be extended to a group. The problem, the differential equation, which we will consider, will be time reversible. So I can retrieve the past in this kind of equations, which will not at all be the case, for instance, for the situation number 1. Some examples. In general, for the self-adjoint, I try to write this in PDE terms. For the self-adjoint case, the problem, the PDE problem, which can be related to this example is the heat equation on a domain. So it's a generalization of the very simple example I have written at the left. So this is for T positive and X in an open bounded set omega. Theta of Tx is equal to 0 if T is larger than 0 and X is on the boundary. The initial condition, theta of 0x is equal to theta 0 of x if x is in omega. So here, the space capital X will be L2 of omega. Assuming that the boundary of omega is also smooth, to write things simpler, but this is not essential at this stage, the domain of A will be W22 of omega cap W10 of omega, 1 to index 0 of omega. My operator AF will be Laplacian F. So maybe I forgot something important. Now that I write it, I forgot something very important. A is equal to A star is not enough to have a semigroup. I should say A is equal to A star and smaller than a multiple of the identity. So A minus M identity should be negative. Because otherwise you can imagine a spectrum which goes to plus infinity. We are real eigenvalues, which it will never work. So please excuse this error. So this operator A, this is how I realize my error. This operator A is negative, is self-adjoint and negative even if omega is not bounded. It will not be strictly negative, but will be negative. This is the self-adjoint, the typical self-adjoint example. The typical skew-adjoint example will be the wave equation with Dirichlet boundary condition and, of course, two initial data. Since I have a second in order in time differential equation. That's for X in omega, I don't write anymore. And here, X will be W1 to 0 of omega cap L2 of omega. Omega bounded, let's say here, with the inner product. That's a useful remark. G1, F2, G2 in X is equal to the integral of omega of gradient F1, gradient F2 conjugate plus G1 G2 conjugate dx. So important, I just take this inner product, which of course is equivalent to the usual one on H1, on W1, 2, due to the Poincaré inequality. But this particular choice is important to make the operator, which has a domain D of A is equal to W22 cap W0, 1, 2 times W0, 1, 2 defined by A of Fj is equal to J Laplacian F, to make this operator skew adjoint. So skew adjointness is really working in the strict sense because I choose this inner product. So that's the typical, and of course, I can add perturbations which are bounded. So here, what can I add as a perturbation? That's the third situation. Roughly speaking, to have it bounded in the state space, I can multiply by a function, add here alpha of x times theta with alpha bounded. That's an admissible perturbation which keeps the fact that I have a semigroup. And here, I can add a bit more since I'm in this inner product. I can add here a PW, where PW contains, let's say, A of x, a vector, times the gradient W. This is a vector, plus B of x dW over dt, plus C of x W, with, let's say, all these three guys bounded. I can do that, and I still preserve the semigroup structure due to the third assertion. So these are some examples. So here is, in fact, I discussed essentially example 6 and example 7 with a bit more details. Now something which is important for control, at least in an abstract setting, it's this space x minus 1, which is called in some literature an extrapolation space. So what is this? I think I can go in the other side of the blackboard. It's the completion. If I have I begin with a classical construction which people working, for instance, in linear elliptic PDEs are very familiar with. I have a dense subspace V of X. Then this subspace has a dual. V prime, which a priori is, as everybody knows, the set of linear bounded functionals on V. This space, we know also by the Riesz representation theorem, is isomorphic to V. But this isomorphism is not a canonic one. I can identify V prime with V. I can identify it with many other spaces. It suffices to choose a pivot space. And that's the notion of pivot space, which here I take not an arbitrary V, but a V included in my Hilbert space X with a continuous embedding, which I forgot maybe to say. I complete V prime with respect to this norm. So somehow I take duality with respect to the inner products of X. So I obtain in this way a larger space, a space which is larger than X, which is called the dual space of V with respect to the pivot space X. So I have people write V included in X, included in V prime, and call this sometimes the Gelfand triple. And it's something which appears, a structure which appears many times. So now, if I take a semi-group generator, A from D of A to X, semi-group generator, then I know that A star is adjoint. It's also a semi-group generator. And so I do this construction for D of A star. So I take V is equal to D of A star. And I do this construction. V space is denoted by X minus 1. In general, I use an X with an index for a space which has already a norm on it. I don't say D of A as a space because D of A priori has to be endowed with a norm. It's just an algebraic structure. So here I take the graph norm here. This one is also denoted sometimes, but I will avoid this notation as much as possible. X1 dual, because there is A star. And I have this construction. Why is this space important? Among other things, so X1 will be D of A endowed with a graph norm, and X1D will be D of A star endowed with a graph norm. Then, in fact, TT can be restricted to X1, still being a C0 semigroup on this smaller space. That's a general fact, and can be extended uniquely to X minus 1, to a C0 semigroup on X minus 1. And these new families of operators are similar to the original semigroup. What does this mean? If the original one was a unitary group, this is also the case of the extended one. If it was a contraction semigroup, it will also be the case. If it was, let's say, a holomorphic semigroup, which I did not define, it will also be preserved. Everything is preserved because these semigroups are just isomorphic. I can construct an algebraic isomorphy between them. So what is this extension? It looks complicated, but in fact, I can make this extension very simple. I have to, I will take F in X minus 1, which is D of A star prime. And how I define the extension TT tilde F will also be an element of X minus 1. TTF, so I have to apply it to G, and this will be a duality X minus 1, X1D, no? These two are dual, will be by definition just F applied to TTG in X. Now, for every G in X1D. Now here it makes sense. TTG is TT star. Oh, G is in the domain of the adjoint. TT star G will be in the domain of adjoint. This is something which lies in the domain of the adjoint. So I can apply F, and I did the extension. And the same, a similar formula holds for the generator. A similar formula holds for the generator. So, and just one word, I will not use the TT tilde. If I take extension or restriction, I will use the same notations. Yeah, I would understand that it can be a restriction or an extension. And I say the formula, the same, a similar formula for A. So a priori A goes from X1 to X. I can define again for every F in X and for every G in X1D. I can say that AF G, A tilde F G, duality x minus 1 x1 d will be equal to F A star G in X. So again, the same, and in this way, this extension A tilde is going from X to X minus 1. So I have defined this extension. Attention, if A would be, for instance, the Laplacian, the Dirichlet Laplacian, yes. Sorry? Which one? Here, the last? Here. So what I want to say, I take an fx minus 1, I want to define tt tilde f as an element of x minus 1. To define it, I have to say how it acts on the elements of x1d. And I say it acts in this way, this formula. And this formula makes sense. Yes. Here it's still duality. Here is still duality, you are right. Here it will be still duality, is not in x, will be x minus 1, x1d, which makes sense. Thank you. Here I think it's okay. Here it will be okay. So attention, if you take the Laplacian, this example where I have it somewhere, if we take this example, we apply this construction, the extension will not be the Laplacian in the distribution sense. We have to be a bit careful. So this duality, it's an operator which, in fact, the dual of the domain is not a distribution space. It's not a subspace, d of omega is not a good space to use here. Okay, so this can be repeated. This can be repeated in both directions, this construction, and we get what some, for instance, in the book of Engel and Nagel is called the towers of Hilbert spaces. So obtain new semigroups which are either extension or restrictions and which are similar by this kind of isomorphism to the original one. We will need x minus 1 very often. We need it, maybe I'll try to avoid it, but I will not always be able to do that. X minus 1 appears quite oftenly in control theory with this viewpoint. Very rarely x minus 2. So let us go to the object to get closer to our object now. I made a lot of functional analysis. Now let me write a differential equation in a Hilbert space. So I take equation 1, z dot is equal to az plus f, with f which takes values in x minus 1. I need to take this in order to tackle a bit later boundary control problems. So what is a solution? A solution in x minus 1, the definition is that it's a function which has this regularity, so continuous with values in x minus 1, and L1 loc with values in x, which satisfies for every t this formula. So this is written in a way to give a sense to all the objects. So z of t, z of 0, these are elements of x minus 1. This equality holds, roughly speaking, x minus 1. Az, here A is already the extension as an operator from x to x minus 1. So Az of sigma, it's a function which of sigma, which is L1 with values in x minus 1. So I can integrate this on 0t, and that's the definition. One of the definition, or equivalently, it is not difficult to check that equivalently, we can ask this formula. This is roughly speaking, making explicit the fact that all the functions take values in x minus 1. But this looks closer to what some people in PDE are accustomed with, which is a weak formulation. And of course, what is more often, so here our spaces are in a certain sense shifted. What's more often encountered in applications to PDE, for instance, in the book of Pazzi, is Fs which take L1 lock in time, which take values in X. Then we define the concept of solution in X, which can be defined very similarly by replacing here everywhere X minus 1 by X and X by X1. It's very standard. Here, we have to be more careful of how we replace in remark 2, but in the original definition, it's all what we have to do. So here I wasn't careful. So we have a theorem, a proposition, which says that for every initial data in X minus 1, I have a unique solution in X minus 1, in the sense of my first definition, which is given by the variation of constants formula. So this is a theorem, which we don't know, it was considered as a very big difficulty at a certain moment. There were the papers which tackled the obtainers of this formula have a lot of quotations to say that because a solution defined by this formula is called mild. So to say that mild solutions and weak solution is the same thing seem to be something which came slowly into the spirits, but in fact it's a very simple proof. We have it in the book. So with this, of course, we can conclude that for our initial value, if I attach to this equation an initial value problem with a z0 in X minus 1, I have a unique solution given by the variation of constants formula. And then if I have an F which is smoother, for instance, W1 infinity lock with values in X minus 1, I will get a smoother solution. So what's interesting here that if you look to in a semi-group context, for instance, let me try a simple situation. Z dot of t is equal to AZ of t plus F of t, and I take F to be L1 in time. I don't care about log so much at this stage. With values in X, in general, Z dot and AZ separately have no reason to be even take me LP, have no reason to be in LP of 0 infinity X. Which, if you are accustomed just to, for ODs, this is clearly true. We know from the OD theorem that this is true. And in fact, it's true. Having this property is called maximal regularity. And it's something which, in a Hilbert space setting, characterizes what's called holomorphic semigroups. So it will be, for instance, true for the heat equation. It will not be true for the wave equation. So the wave equation is a good example where this is not true, but we can construct other ones. So here there is a particularity of differential equation with the source term, which involve a general semigroup generator. So I can now go to the main subject of the today lecture, which are well-posed control linear LTIs. LTIs meaning linear time invariant system. So as for semigroups and their generators, we have two possible approaches to define firstly the solution operators and then to obtain, in a certain sense, the generators, or to begin with some operators and then to construct the well-posed linear system. Yes? I'm not sure I understand. So I consider this equation. Let me take it 0 here, the initial data. And I take an f which is LP of 0. So the difference of z dot and AZ lies in LP of 0 infinity x. But as I said, that this what I wrote here, it's true for the heat equation for holomorphic semigroups. It is not true in general. That's what I'm saying. So this is another general fact, and in fact, we can prove that in the Hilbert space setting, this holds if and only if A generates an analytic semigroup. It is a known result. In the Banach space, if X is a Banach space, then this maximal regularity property is not equivalent to the analyticity of the semigroup. It's even stronger than the analyticity of the semigroup. As we will see later, these well-posed linear systems are generalizations of the concept which will appear immediately, in fact, also on the slides. On a simple system which will appear also on the slides, which is the finite dimensional systems, linear ones. Z dot of t is equal to A Z of t plus B U of t, with A an operator from Cn to Cn, and B an operator from Cm to Cn. Then we know by the variation of constants or Duhamel formula that Z of tau is equal to exponential of tau A Z of 0, which I will call, this will be my semigroup. It's an example of semigroup, plus the integral from 0 to tau of exponential of tau minus sigma A B U of sigma d sigma. And this guy, we will call it phi tau u. But in this approach, which is, this is in a certain sense what I wrote here, is an example of the concept which I have written on the slide. So first some notation. I have 3 Hilbert spaces. In fact, I need only 2, U and X. No, X, yes, U and X. U is called the input space, X is a state space, and I can have an output space, which I forget about it here. Sigma tau are maps, two family of maps, T tau, which maps X to X, this is a semigroup, and phi tau will be the other one, which is called output map. So beginning with an A and a B as here can be a good start. But what we want is to begin with these 2 families, as I did with semigroups. So to do this, I introduce this notation, which is concatenation. It's clear what this is. I have two signals U and V defined on 0 infinity, 14 0 infinity. What I do here is I take Q up to tau, and then I shift T, and I begin V from tau, as it would begin from 0. That's concatenation of 2 signals. It's a very standard concept. The notation is maybe less standard. And so I say that 2 families of this kind form a well-posed linear control system with state space X and input space Y if, firstly, T is operator semigroup, and then the family phi T satisfies this formula. The basic example being, of course, if U and X are finite dimensional, which I wrote there, to take exponential here and this convolution for phi T. But I can begin with these two concepts. So it will be sometimes useful, at least for definitions, to design a system. So I will, for the moment, design a system by these two families of operators. So what does this formula say, roughly speaking? It looks a very complicated thing, but in fact, it is extremely simple. In fact, first, what is this approach? So this approach is inspired, in fact, from control engineering. That's how a control engineer would see more intuitively our system. You maybe saw some pictures, how they represent at the beginning a system. So a system is a box. This is a system sigma, in which you put an input, which is a function u, and you get in principle an output, which here will be the whole state. The state of the system will be my output z, let's say, and then possibly, which I will not do here, we measure the output and we come back with a feedback, which is very interesting for applications, but we will not discuss here. And so now let me see let me comment one moment this very simple formula. What is the maps phi t are called the input maps. What does input map means? It means that I have no initial state equal to 0, and I just measure the state produced by my input at some instant. That's the input map. So let's say here I have t. Here I have a tau, let's say. Here I have tau. And here I have tau plus some t. What is phi index t plus tau of u concatenated to v? It is, in fact, I apply this concatenated, so here is z, signal. So I leave from 0, and I reach somewhere. This will be phi tau plus t of u. What does this formula? So this is the left-hand side, the representation of the left-hand side. What is the right-hand side? It's even says that for that I can reach the same point in the following way. Okay, I first reach here, and here I will have phi tau of u. And then from this, if you imagine that I have this system, I take this as initial data, and I apply the variation of constants formula. So this is an axiomatic, let's say, transcription of this variation of constants formula, nothing more. It turns out that there is a theorem, not very well known due to Weiss, so it's very known, it has a huge number of quotations. In some communities it's very well known, but not in the PDE community, which says that such a well-posed system necessarily represents as z dot is equal to az plus bu, with b, which goes from u to x minus 1. That's important. That's why I need x minus 1. He shows that B necessarily should be allowed to go in larger spaces. Of course, B could be various in X. We have a lot of examples, but this is not mandatory. Okay. So I will not comment this proof. It's not very complicated. There is a reference of the original paper at the end of my presentation. And so we can ask now the question in the other sense. I have an A, which is semi-group generator, A and B with values in x minus 1. Then I should ask explicitly these quantities to take values in x to have a well-posed system. And that's how I introduce the concept of admissible control operator. I say that B from U to x minus 1 is admissible if this quantity, which a priori lies in x minus 1, takes values in x. So the quantity which I'm integrated here for almost every sigma lies in x minus 1, but the nice thing which happens with admissible control operators is that when I integrate, I go to the more regular space, capital X. Of course, not every operator from U to x minus 1 is admissible. So here we have to. So in a certain sense, if I know that I have the system, I know that the B will be admissible, if I were possible. But how should we prove that we have the correct properties of the system? That's another issue. And now I will go quickly to some through a characterization by duality. So how can we prove in practice when we have a B? We will see that in practice, giving the B is not always very simple. But supposingly I have a B, how can I check that it is admissible? One way is to explicitly solve my problem, and I hope fight out. This is rare in application. And a remark which is useful is that it can be characterized by duality by this inequality, which in control theoretic terms is translated saying that B star is an admissible control operator for the adjoint semigroup T star. So here, so first, the proof of this is very simple. It's not a big question. It's roughly speaking, for instance, if you assume that phi tau takes values in X, you compute its adjoint, and you will see that it's essentially this operator. So an operator is bounded if and only if it's adjoint in bounded, and this is essentially what it said here. Of course, there are technical details. But here I didn't write more operators, because somehow this is something I can write without complicated stuff. So here, since I can, let's say, limit myself to f in d of A star, all the operators are in a classical sense. But with a certain, with a certain, let's say, care, which is necessary, when we compute these adjoints are computed here when I wrote this. So I have a priori, for instance, B goes from U to x minus 1, which, let me remind, is the dual of x of d of A star with respect to the pivot space X. So what I wrote here on the slide was that B star is from X1 to U, X1D, so or D of A star. What does this mean? That in that formulation, we identify most of the time U and U prime is dual, and X with X prime. So if you do, for instance, identify X with its dual, you can no longer identify X1 D of A star with its dual. You are obliged to use duality with X with the. But of course, this would be true for every duality. Sometimes, we'll have an example, we prefer not to identify X and X prime, for instance, namely for wave equation problems. But this is the most natural thing to do, however, and to my knowledge, is what's done in most of the examples. So Here we took duality with respect to the pivot space X and U also. But here I don't have subspaces of U. For the moment, I don't need to take it as a pivot space. So now I go to some examples. So I begin first in detail with a very simple one, but where I would like to have formulas, and formulas which are a bit unusual for the heat semigroup and for the corresponding input map in 1D. I will then come back and do comments immediately on several space dimensions. Maybe I should begin with this for the heat, but I'll see after in terms of the time. So let me take first, I will take two situations. The heat equation on half line, 1D. And I put a Dirichlet boundary condition at the left end. So can I associate a semigroup to this? The answer is yes. This semigroup, I call it T tau left, because the boundary condition is at the left, and it's given by this formula. How do I get this formula? It's just that if I had only the first quantity here times psi, this quantity is a heat kernel. And then I just symmetrize to satisfy the zero boundary condition at zero, and I get this formula for the solution. So I have a formula of my semigroup, fully explicit one. And so what I should maybe say is that, okay, so this this formula is the particular case of, so the semigroup is a kernel operator, in fact. No? And it has the form T tau psi at point X is equal to integrals or T psi, doesn't really matter, let's not of K of some integral from 0 to pi, of no, to 0 to infinity, of K of tau x, y, psi of, let me put G here, psi of y dy, where you see which is the formula of G. The formula of G is a kernel which appears there. No? That's what I try to keep for the moment. And now I want to associate to this a well-posed control system. So what I put a Dirichlet input at the right. That's not the best case to have a Dirichlet boundary condition, but it's the one I will need tomorrow. Because here you can wonder, so, yes, so as I mentioned here, the choice on the space on which is a semigroup is multiple. I could choose W1, 0, index 1, 2, index 0, L2, or W minus 1, 2, which is the dual of that. And this will be the choice which will be done later. Because this problem, roughly speaking, when I take initial data 0, so very good, and I take U in L2, my solution will not be continuous if there is in L2. Will be less regular than that. How can we see that? For instance, we compute it for regular solutions, and then we look if we can extend the operator. So the proposition 3 says that this determines a well-posed linear control LTI, T left, phi left. T left has already been defined in proposition 2, and phi left is given by this formula. So I have everything explicit in terms of this kernel. How do I do that? There's maybe worth to see So I say, okay, how I know this formula of the semigroup. So I write first. So which is the notation? This is the formula for phi of t and x. So, and here I would have phi t. This is phi of t and x, the solution of this problem, with phi satisfying d phi over dt minus d2 phi over dx2 is equal to 0. Phi of t0 is equal to 0. Phi of psi x is equal to psi of x. So that's phi. And in fact, what I'll do, I do here, I will reverse the sign, the change of time by keeping the notation phi. So I replace t by tau minus t. So I will get here plus. I take the backwards problem. Phi of tau that's the same here. T0 is equal to 0, and phi of phi of tau 0. What is this? Phi of t0 is equal. Here it was 0. In fact, it was a mistake. Now it will become phi of tau x is equal to psi of x. That's the backward problem, no? Whose solution will be, if I do this, the only difference will be, I'm erasing here, sorry, I'm erasing this, replacing by phi of tau x, and here I will get tau minus t. Just took the backwards problem. And then what I will do is to write the equations which I have here. And I will believe if everything is smooth, I have a smooth solutions, which is not so, let's say, unbelievable. And then what I do is I multiply, assuming this, I multiply first equation in 6 by 5, each term. So I do integral from 0 to tau, from integral from 0 infinity, and I integrate everywhere. It's a classical duality argument. To find the solution. Here I'm using it just to compute the solution. dx dt is equal to minus integral from 0 to tau, integral from 0 infinity of z d phi over dt dx dt plus a boundary term, I integrate by parts in time. It will be z phi at instant tau. It's nothing else as z of tau and x, psi of psi and x. So this will come with a sign plus. Plus z of tau and x, psi and x. And at 0, it is 0 because because I take also initial data 0 here. I take also initial data z of 0 and x is equal to 0. I want to compute phi tau. Phi tau is nothing else but the solution of that with initial data 0. No, I want to compute phi tau. Okay, so I do this simple integration by parts. What about another one? The second term which appears in the equation for z, d2z over dx2 phi, dx dt. Here I integrate twice by parts with respect to x. It will be, since it's twice, I will have the sign plus. Okay. And I have some boundary terms. When I integrate once, I will have dz over dx phi, but this one will vanish at both ends, which will come with plus. So I will have with minus, so dx dt, minus integral from 0 to tau of U of t phi of U of t d phi over the x at t0 dt. And now, if I do the difference between the two, I will get that z of tau and x. So the left-hand side is vanishing. And I will get that z of tau and x. It is with the sign plus, no? This plus this is equal to 0. So it will be equal to minus integral from 0 to tau of u of t d phi over dx at t0. And now, if I replace phi with this, I get exactly my formula. And because psi is arbitrary, I get exactly this formula tested with an arbitrary psi in L2. The calculation is immediately here. This quantity is, which I here, is nothing else than the derivative of my kernel with respect to x evaluated at y equal to 0. So that's how I get this formula, which will be important. So as is mentioned in the title, one of the things which we are interested in these lectures is to find the reachable space. Or the reachable space is the range of phi tau. By definition, I will formalize that, of course, next time. It turns out that this one, the range of this one, we can really compute it. We can say exactly which is the range of that one, which is very rare in partial differential equations systems. Now, the example, which is the main one, and which I already shown the semi-group by Fourier series, is the heat equation on an interval. Here, it turns out that writing like this with Fourier series has been extremely useful for many purposes, namely for control theoretic purposes in the famous papers of Fattorini and Russell. But for these reachable spaces stuff, it's more convenient to write the same object in a completely different manner. And so firstly, my semigroup is given by this formula. So which is a series, so my kernel here will be a series of Gaussians, if I look carefully. So it will be convolution with a certain kernel, but the kernel is defined as a series of Gaussians. Again, you remark the heat kernel, which appears in various shifted manners. So how do I prove this? So where did I write something? Let me go further. In fact, the proof is essentially here. It's very simple. It's called the method of images in the PDE literature. And it's not very complicated stuff, especially in 1D. So what I want is to solve, I have here 0 pi. I want to solve my initial value problem with the initial data psi in 0 pi. If I want smooth solutions, which is let's say the initial framework, I should take an initial data psi, which vanishes at both ends. That's what it wants. It's smooth, but vanishes at both ends. So I want a formula for the solution with this kind of initial data. This is just a semi-group. I have homogeneous boundary condition. And then what I do, I extend by oddness. What does it mean? From pi to 2 pi, I will not make the best possible picture. And then I come back here. And I continue. So it's not by periodicity Or if you want, I have a periodicity of 2 pi, which appears here. And I do this both to the left and to the right, infinitely. And I obtain a function psi tilde defined by this formula. So that's the extension by oddness to a function of my initial data defined on all of R. And then what I do, I solve the heat equation with this initial data, but the heat equation, the Cauchy problem. So I take this one as initial data on all of R. You will tell me, oh, but this is not bound, not in a Sobolev space. It's not a problem for the heat equation. I have a unique solution, which is still given by let's say, the extended theta tilde psi tilde will be by definition, by the known formulas, the integral from minus infinity of k, the heat kernel, which I denote, let me denote it k tilde of exponential. I can write it explicitly, 1/2 square root of p tau, integral from minus infinity of exponential of minus x minus y squared over 4 tau, psi tilde of y dy. So an integral over R of psi tilde. Of course, I'm interested just for x between 0 and pi. But the formula is valid for every R. And then the formula which I written here, it's exactly that one. It's exactly that one, or what I am doing. I'm doing change of variables, all the integrals from, for example, p to pi, 2 pi, 3 pi. I bring them on 0 pi by change of variables, which makes me shift the kernels. So that's all in obtaining this formula. In our paper, so it turns out that I didn't see it explicitly somewhere, but it's not a big stuff. In our original paper on the first paper on the reachable space, we have reproved it by using the Poisson summation formula. So we took the original formula with Fourier series, and then we applied the Poisson summation formula, which is also a way to do it, but I think it's less nice than that one. And so now again, I have a kernel, convolution with a kernel. This kernel is a series for the semigroup, and I can obtain the input map. The input map, which is obtained just, in fact, integral from 0 to tau, normally is the derivative of the original kernel with respect to x at this point, convoluted with the boundary data. So here I have 2 boundary data. So I separately solve for each one, and I have phi right. Phi right here is, in fact, it said here what is this k pi. So firstly, there are 2 things to mention here. I separate in the sums, which will appear, m equal to 0, m equal to, which are in phi tau left, and which will give me the phi tau left, and it's symmetric with respect to pi over 2 for yp. So this is the terms which correspond to m equal to 0, and all the other terms which are in these kernels and which are defined by the shifted Gaussians. Okay? And all this is converging in the Sobolev space W minus 1, 2 in a very good manner. So this is a formula which is important and even if it's very simple, and it's at the basis of what we will see on the reachable space of the heat equation. So what to say about already this example, heat equation in several space dimensions. What's simpler to speak about is the Neumann boundary conditions. If I now go to the following situation, omega in Rn open and bounded. Is not essential, the boundedness, bounded. The boundary of omega, let's say at least C2, but it's just for simplicity. And I consider the boundary control problem, d theta over dt minus Laplacian theta is equal to 0 in 0 infinity times omega. Theta is equal to an input u on 0 infinity, no, not theta, I will come back to that, but this is more complicated. The normal derivative of theta is equal to u on 0 infinity times the boundary of omega. Then what will I call solution? So this can be written as a well-posed linear system with x is equal to L2 of omega. U is equal to L2 at the boundary. A is the usual A, or minus A. No, A is the Dirichlet Laplacian. With usual domain, I don't say anything more. So here, that's why this example is nice. And B, defined in the following way. Bu applied to phi. Duality. B will not be with values in X, but Bu applied to phi x minus 1 x1d is equal to integral over the boundary. So in fact, I can write here the duality more explicitly. W minus 1 to W1 to 0 is equal integral over the boundary of u phi, the gamma, for every phi in W1 to 0 of omega. So I define it by duality. And how does it come? It comes very simply from the weak formulation of this problem, no? When I write the weak formulation of this problem, it's immediate, that it is d over dt of theta phi plus, I can say, here we, maybe to keep, I write it minus for the moment, I write it minus theta. For phi in this cap, let us put it, even if it's not necessary, cap W22 of omega here for phi. So I take minus theta Laplacian phi, this is the inner product L2, plus, I think it will be, or minus integral over the boundary of omega of u d phi over dn d gamma is equal, no, u phi. D gamma is equal to 0, no? For every test function in W1, 1, 2, no? I just multiply by a test function phi in W1 to 0, kept W2 to. I integrate by parts twice. I have this formula, and here, this is Bu phi. So the B, I can define it very simply by duality. In fact, it's the Dirac mass concentrated on the boundary. In 1D, it will be the Dirac mass classically at these points. So this is quite simple. Why is simple? Because I could choose the state space to be L2. Yes. Correct, Neumann Laplacian. Thank you. So the domain is W22 with normal derivative vanishing at the boundary. So here, if I do the same thing with here theta equal to with Dirichlet boundary condition, then I will no longer be able to do the same thing. So if I consider this is something which is more technical, I prefer to avoid, even if somehow we have done it in, unless 1D. In 1D we have done it. It's in a almost, let's say, complete way. So I take d theta over dt minus Laplacian theta is equal to u. I don't write, so again, on 0 infinity of times omega. Theta over the boundary is equal to u, so that's Dirichlet boundary condition. Here, unfortunately, if I choose u to be, I can begin by choosing q, which is a natural choice. Here I don't have much choice in general, to be L2 at the boundary. I cannot choose x to be L2 at the interior, because simply my solution will not take values in this space. I can choose it to be W minus 1, 2 of omega. In this case, roughly speaking, the B operator, it's more difficult to say, but I write the formula. A is again the Neumann A will be this times the Dirichlet Laplacian, not Neumann. But from W1 to 0 to W, so in this space W minus 1, 2, with domain W0, 1, 2, and the B, to write a B, the usual way of writing B is to say that B is A applied to du, where du is what's called the Dirichlet map. How is defined du? Laplacian is a function which satisfies in the distribution sense. Laplacian of du is equal to 0, and du in omega, and du on the boundary is equal to u. Well, in 1D, this du is nothing else but the derivative of the Dirac mass concentrated on the boundary. It's the derivative. So for Neumann, it was the Dirac mass. For Dirichlet, it's the derivative of the Dirac mass. It can be said like this also in several space dimensions, but the most convenient way is to introduce this Dirichlet map, which has a property that D, in fact, if you take a boundary condition in L2, your solution will be better than L2, but all what we need here is to say that it takes values in L2. No? You know that when you solve a Dirichlet problem, you win 1/2 in the regularity scale. Here it's more complicated. Besides the 1D, I will not speak about that, but in 1D, roughly speaking, BU in 1D will be up to a sign d delta 0 over dx and d delta pi over dx. Will be this operator. Okay, so this is for the heat equation. I will soon end. What about the wave equation? Let me show you a simple example with the wave equation. Maybe Belassen will speak about the boundary control of the wave equation. I will speak about a very simple example, a string equation with a pointwise control, to have really something which is very easy to understand. Is equal to 0, so that's a string equation. t positive, x again in the interval, no, not 0, is equal to, I add as a pointwise force. So I have a string, imagine a violin string. You want to play some music, and then you push with your finger at x is equal to x equal to psi, and you assume that you just push up 1 point, which is of course not necessarily realistic. 0 pi. So here it's clear what's and I put Dirichlet boundary condition. Here it's clear the choice. This is why I prefer this example. The choice of the space is immediate. X is the W12 function vanishing on the boundary times L2. And U is just C, let's say. It's capital U is C. And BU, the semigroup will be the wave semigroup in 1D. I will write it maybe immediately, but not exactly. And BU will be 0 U times the Dirac mass concentrated at C, when I write this as a product space. And so the question is this an admissible control operator? It's clearly unbounded. It goes out of L2 for the second component, no? So why is it admissible? Here I reason by duality. By duality, I should write what is T star, B star, and so on. B star is very easy. B star, it's defined on U with values, and that's important, in values in the dual of this guy. So here I identify X with itself, as usually. So it will be X. And B star U will be 0. No, B star U, B star not U, phi psi will be equal to psi of psi, the second component. So the inequality integral from 0 to tau, which is by duality necessary, B star, TT star, phi psi, or let's put here FG. Here, let me put FG here, G of psi, and here phi psi, smaller than k tau squared. The question is, do I have this inequality? And if I do the computation, what is this? When I compute the adjoint, I will solve the problem, which is obvious. I have here a skew adjoint problem. I will have a wave equation, homogeneous, with phi of t0 is equal to 0, phi of t pi is equal to 0. And I want to measure integral from 0 to tau of d phi over dt, the second component, at xi and t squared. I want to see that if it's this is bounded by the initial by the norm of the initial data in x of x. So here maybe the notation phi psi is not very good. Let us put v. The initial data will be phi psi for this. And then I say, okay, I would remark, if I take here my initial data, phi is equal to phi of x sum of an sine nx, and psi of x is the sum n larger than 1 of bn sine nx, then v of tx, so the solution of this problem, by simple Fourier series, is the sum of an sine an cosine nt plus bn sine nt, everything, times sinus of nx. It's a very simple computation. So I just solved the wave equation with homogeneous Dirichlet boundary condition on 0 pi with this initial data. And then what will be this? This, what I'm doing, I'm taking the derivative with respect to time, and I'm taking x is equal to xi. So it will be equal to integral from 0 to tau. When I take derivative with respect to time, I get minus n an sine nt plus nbn cosine nt, everything multiplied by sinus of nxi. So I have to look to the integral of this sum. Of course, there is a sum inside. Integral of the square of the sum, no? dt. And this is clearly up to a constant, smaller. I just apply Parseval now. I just apply Parseval. Sinus of nt, cosine nt are orthogonal on 0 to pi. Of course, my interval is not 0 to pi, but here I have an upper bound. It really does not matter. If it's smaller, everything is okay. If it's larger, I just use periodicity. So this will be smaller than some constant, sum of n2, an squared plus bn squared, and I'm done. Because this is exactly the norm of the initial data, again by Parseval, in the space I want. So this is an example with the wave equation. Of course, this delta xi can be pushed to the boundary. If I push it to the boundary, I obtain Neumann boundary control. If I push it to the boundary and take the derivative with respect to x, I will obtain Dirichlet boundary control, but the state space changes. So I'll stop here. Thank you very much for your attention.
So in the heat equation with Dirichlet data, so why finding B is difficult? I mean, that B of U, that plus minus of that things.
It's not difficult, but it's more difficult because I cannot take the pivot space to be L2. So I have to turn around a space which is larger than L2, and then this duality is more complicated. That's all. Is that unfortunately we cannot choose L2 as a state space. So the solution with Dirichlet L2 in time data is less regular than the solution with Dirichlet Neumann, with Neumann L2 with the same regularity, which is normal because I'm asking the derivative to be regular, to be L2. With Dirichlet, I'm asking just the function to be L2, which gives less regularity at the end. So it's a matter of regularity, and then as an implication, a matter of duality with respect to an appropriate pivot space. Thank you.